Welcome to This Explainer. Today, we're unpacking the truly fascinating journey of how wild, unpredictable AI models are tamed into the highly capable, conversational assistants we literally rely on every single day. If you've ever wondered how these massive systems go from spitting out random text to carefully answering your complex questions, well, you're in exactly the right place. We're going to break down the actual engineering roadmap used to tame the AI beast.
Before we get into the advanced engineering, we've got to start with a fundamental question, straight from our source material about early AI models. Can we do better? See, early language models were trained on massive, mostly unlabeled datasets just scraped off the web. Their primary directive was overwhelmingly simple. Just figure out the next word. And yeah, while this let them learn incredibly rich word associations and do pretty well on basic tasks, like finishing an idiom or mimicking a writing style, they fell incredibly short everywhere else. If you tried asking one of those early models to actually do something for you, you'd hit a brick wall. They were notoriously, and honestly sometimes hilariously, bad at following explicit human instructions.
So here's the exact roadmap engineers use to solve this, layer by layer. First, the AI misalignment problem. Second, instruction tuning. Third, learning from human feedback. And finally, chain of thought prompting.
Let's kick things off with Section 1 and expose the fundamental flaw in base language models, the AI misalignment problem.
The crucial point here is that default models just optimize for next word prediction, and that leads to massive misalignment. Because their sole objective is just to guess what text comes next based on raw web data, they often generate wildly unintended outputs. We're talking about fabricating facts out of thin air. Ask a base model for a biography, and it might confidently invent a historical battle that never actually happened, simply because the words statistically fit together. They can also spit out biased or toxic text found deep in their training data, or, just completely ignore what you actually asked them to do entirely. It's a clear, undeniable misalignment between what the AI does and what we actually intend.
Now, traditionally, engineers tried two rather expensive workarounds to fix this. You could use standard fine-tuning, which typically requires massive amounts of task-specific examples. To do this, you essentially have to build and maintain one specialized model for every single task you want to accomplish. As you can imagine, that is incredibly expensive and highly inefficient. Or you could try few-shot prompting. This tries to improve performance without changing the model's underlying weights by basically stuffing examples right into the prompt. But you're constantly battling limited context sizes and incredibly high computing costs. The industry desperately needed a much more universal solution.
Which brings us to Section 2 and our first real, scalable solution, instruction tuning.
Instruction tuning represents a massive leap forward in capability. Instead of just predicting words or fine-tuning on a single narrow task, the model's fine-tuned on explicit natural language instructions across dozens of different tasks simultaneously. By feeding the model varied prompts like summarize this paragraph or translate this phrase, the model actually learns the core concept of following instructions. And why is this such a game changer? Because it allows the model to generalize to completely new, unseen tasks in a zero-shot manner. It means the AI can successfully do things it was never explicitly trained to do just by deeply understanding the nature of the command itself.
Moving right along to Section 3, learning from human feedback. What exactly is RLHF?
To understand this, let's do a quick refresher on reinforcement learning terminology. Think of the agent as our AI student. This is the language model itself actively trying its absolute best to figure out the right actions to take to achieve its underlying goal.
Next up is the environment. This is the context. Essentially, you, the user, or the system where the AI's generated text actually lands to be evaluated. It's a dynamic space that shifts constantly based on the prompts and constraints we throw at it.
Then we have the reward. This is the all-important good grade given to the AI. It's the ultimate feedback mechanism for value alignment. When the model generates text that perfectly aligns with our explicit intentions, like being genuinely helpful, and our implicit intentions, like staying truthful and non-toxic, it receives a high reward.
And finally, the policy. This is the internal strategy engine the model updates and uses to consistently maximize those rewards. The entire goal of this complex process is to optimize this policy so the model naturally defaults to the behavior we humans actually prefer, all without needing constant correction. When we put this all together into a continuous cycle, it looks like this. The agent acts by generating text, the environment observes it, and a reward is calculated and fed straight back to the agent. This feedback loop is the true engine of alignment. By running through this cycle thousands upon thousands of times, it constantly pushes the AI to refine its policy, generating better, safer, and remarkably more helpful responses over time.
So let's look at how this heavy machinery actually works in practice. The source breaks this down into 3 distinct, sequential steps to finally conquer misalignment.
In the first step, we start with basic supervised fine-tuning to get the model heading in the right direction. But the real magic happens in step 2. This is where armies of human labelers actually step in to read and rank different AI responses based on preference. This massive trove of human preference data is then used to train a totally separate reward model. Then, in step 3, we let the main language model generate text. But instead of a human checking it every single time, the reward model automatically scores it based on what it learned from those labelers, and the main model updates itself to get higher scores. This methodology allows human preference data to act as an automated, highly scalable reward signal to fine-tune the LLM to be both helpful and truthful.
But let's be objective here. Our sources highlight some massive hurdles. As incredibly powerful as RLHF is, it's a remarkably complex engineering procedure. Balancing 2 massive, separate models, fitting the reward model while keeping the main model stable during reinforcement learning, requires incredibly delicate hyperparameter tuning. It can sometimes be highly unstable, extremely inefficient to run, and honestly represents a profound engineering nightmare for even the best research teams to pull off correctly.
That brings us to Section 4, Chain of Thought Prompting.
Because here's the thing, even with advanced training like instruction tuning and RLHF, how we communicate with these AI tools at the user level still matters immensely. Chain of thought prompting is a highly effective method that forces the AI to essentially show its work. Instead of just asking for a direct answer, we engineer our prompts to break complex problems down into smaller, digestible steps. The source notes that this drastically improves performance across the board, specifically unlocking brand new capabilities in really difficult areas like arithmetic, common sense, and advanced symbolic reasoning.
Notice the difference in approach here. A standard prompt is often vague and leaves the AI jumping to conclusions in the dark. It basically has to guess the final output in a single computational leap. But a chain of thought prompt explicitly details the reasoning process we want the model to take. By forcing the model to generate the intermediate steps, like evaluating the lightning, then consciously comparing indoors to outdoors, it provides stepping stones. This drastically improves the model's logical flow, its output accuracy, and its overall reliability.
And honestly, it can be even simpler than that. Just adding this remarkably simple phrase, "let's do it step by step," to your prompts can work absolute wonders. The research shows that complex reasoning tasks often have multiple valid paths that lead to the correct answer. By instructing the model to take it step by step, you actively unlock these reasoning paths. It gives the model the processing space and the tokens it needs to build a concrete logical chain, which ultimately results in a much higher agreement and confidence in the final, correct answer.
Which brings us to a deeply fascinating endpoint. As we construct these elaborate reward systems using RLHF and guide the models with explicit, handheld reasoning chains, we really have to ask ourselves, are we truly teaching AI to think and reason on its own? Or are we just training it to become a highly sophisticated, mathematically perfect mirror of our own step-by-step preferences? That wraps up our explainer on the incredible evolution of advanced large language models. It's a stunning technological leap, leaving us to wonder just how deep this illusion of reasoning truly goes. Thanks for joining us, and keep exploring.